Hi everyone, and welcome to the Savings and Loan Study Guide Part 1. So we're going to be going over both savings and loans today, and you'll see how very similar they are. We're going to go through and look at all the formulas that we have to use, and then in a separate video and on a separate document, we'll be going a little bit further with loans and using Excel. So I'll talk to you about that right at the end. So to start off savings, we're going to start off with this idea of compound interest. And so what's happening here is you put money into a bank. This is the most common situation to be thinking about this. You put some money into the bank, and the bank says, all right, thanks for the money. I'll keep this here. I'm going to go use it now. And because I'm going to use it to try to make more money, I'm going to give you some back. And so that's this idea of the interest. They're giving you some money for you letting them use it. So how does that happen? How do they figure out what to give you? What does that look like? Well, it's actually really nice. It's just percentage increase. So all they're doing here is percent increase. They take your money, they apply a percentage, which is usually told to you when you sign up for your bank account. Things can change, of course, but when you first sign up, you'll be told, okay, in this account, this is the rate that we're going to give you. And so that means when you put that money in, they apply a percent increase to it. And then they just take that amount and they put it into your account for you. So it's almost like you're loaning them the money, which is why hopefully you can start to already see kind of, oh yeah, savings and loans. These ideas are very similar. When you put money to a savings account, it's almost like you're loaning the bank the money. And so they're giving you a little bit extra so that they can go use it. So let's check out what this looks like. So I have an example here. The first example, example 1, says you put $1,000 into a bank account and the bank gives you an annual interest rate of 10% compounded yearly. The word compounding is the action of them putting money into your account. So the action of compounding is actually the percent increase. So when I say compound, you should think, okay, let's do the percent increase now. Compounding yearly means the bank's going to do it once a year. So you put $1,000 in, you wait a year, and then after that year, the bank's going to go, okay, let's do the percent increase. I'm going to give you some more money now. Okay, so what does that look like? Well, to start off, so this is to start, you have $1,000 in the bank. So that's how much you have in the bank. Okay, so after year 1, so year 1 happens, what do we do? Well, the bank says, okay, I need to compound. So I take your $1,000, okay, and then I'm going to, this is percent increase, I'm going to increase it by 10%. We know how to do this, right? We talked about 2 ways to do this. Either we do 10% times your 1,000. That's one method of doing this, right? Or the second way to do this was to just take your $1,000 and multiply by 1.10. You're going to see in a second why I've been trying to kind of nudge you towards this second way of doing it, even if it feels less natural. You'll see in just a second. So either way you want to do this, Unit 1, Unit 2, up to this point has been fine. And either way you do this, you will still get the same number, of course. They're the same thing. So you're going to end up in your bank account with $1,100. Look at that. We made some money just by having money. Look at that. So we made $100 after year 1 because of the compounding interest. Okay, so year 2. What happens in year 2? So year 2, what happens? The bank says, okay, well, you have $1,100 into your account. We haven't touched it yet. Do the same thing. I'm going to increase it by 10% again. Of course, you can do it this way here, right? You can just keep building and building and building like that. But I'll show you why you should start thinking this way instead. So, okay, great. You do this, you set this up, you type into your calculator $1,100 increase by 10%, that's going to leave me with $1,210. So you're like, great, I just made more money. And then you might notice, wait, I made more than last time, right? What happened here? Year 1 to year 2, year 0, if you want to think of it that way, to year 1, I made $100. But actually, from year 1 to year 2, I made $110. Well, it's 10% every time. Percent increase, 10%, that's not changing. But since you have more money in the bank, 10% of more money is more money. And so that's the effect that you get when you start thinking about these savings accounts or investments in general, is that if you get into a situation where your money starts growing, it compounds. It grows, and then that growth grows, and then that growth grows, and then boom, 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 everything starts growing. And so you start to get more and more and more each year. That's the idea of compounding. It compounds. So, we could keep doing this, right? But here's the problem. So scary formula down there. Here's the problem. This works, but what if I wanted to fast forward to the year, I don't know, what year would we want to get to? Year 50. So let's say I'm in year 50 here. How would I calculate how much money I have? If we just do it by hand like this, oh man, look at what we got to do. We got to multiply and then take this number, multiply. Look at how many times you'd have to do that to get from 2 to 50. Don't want to do that. Too much. So we need a formula that somehow gets us to this. Let me do one more example with year 3 now, and we'll see, hopefully, what the formula looks like. So you had $1,210, now increased by 10% again, which is just multiply by 1.10, always that same thing. Okay, 1210 times 1.10, I now have $1,331. And just for consistency, we can go here and say, well, did it work? Did we actually get more money this time? And so when we type this in, we can just do the difference of these two, and we actually now got $121 more. So, this is going much further than you necessarily need to go, but you could kind of keep going here. Watch this. First year, I went up $100. Second year, I went up $110. That's an extra $10. But look at this. Between year 2 and 3, even that is increasing faster. Here to here, I went up $11. So I know that this is a crazy idea to think about, but the change of the change is going up. So not only am I increasing the amount of money I'm getting each year, extra from the compounding, but that extra money I'm getting each year, that's increasing, and it's increasing faster and faster. So that's why you always are told, save early, save for retirement early, save early. Because if you do that, and you can see it in the math right here, if you save early and you are able to let that money grow for many years, the growth seems small maybe at first, but then it really starts to pick up and build steam, and then it grows and grows and grows, and then it gets bigger, faster, and really starts to grow after a little while. And so that's why time is so important here. That's really the big thing. Is out of this, what you need to really kind of get a feel for is that time is the thing that is really helping you here. So that's why the advice is always start saving for whatever you want to save for as soon as you can. Even if it's not a ton, that money will grow by just being saved. Not if it's under, your bed or in a piggy bank, but it'll actually decrease because of inflation. But that's not something we're going to talk about. Put it into some kind of investment with a good enough return on it, a good nice percentage, and grow faster. So how do we find a formula for this? Well, what we're going to do is we're going to try to see if we can find a pattern. So let's kind of go backwards for a second. Where did we start? We started at $1,000. This was our start. All right. Okay. So just follow through with me. Year 1, what did we do? We multiplied by 1.10. All right, we got to year 2. What did we do? We multiplied by 1.10. Year 3, what did we do? We multiplied by 1.10. Year 4, what do you think we're going to do? We're going to multiply by 1.10. And so because we're just doing the same multiplication over and over again, this is actually really pretty nice to put into a formula. And the really nice thing is that every year that we do this, we just get an extra copy of this. So this was after year 1. Now this one, there's now 2 copies after year 2, 3 copies after year 3, 4 copies after year 4. So then, this still doesn't look nice, but remember, if I multiply the same number over and over again, that's the same thing as taking the $1,000, multiplying by 1.10 to the 4th power here. So this multiply, it seems like even that might be a lot to write out, but we have a solution to that. Using the exponent is the same thing as saying multiply, all these things together. So if you think of it that way, then the formula just falls out. Every year I go, I get an extra one of these. And so what does the formula become? If I want to do this at year 50, what do I have to do? Well, I start with $1,000, and then each year I add an extra one of these 1.10s. I multiply by another one. And so all I've got to do is take my 50 and put it up here. Because seeing this pattern, I know, okay, I've got to multiply by that 1.10 50 times. So you could put that in your calculator, 1.10 to the 50th, and you're going to end up getting, switch back to purple, 117,390.85. We'll round at 2 decimal places. Check that out. Put $1,000 in. 10% is quite a nice return. This is not really a realistic return for a bank account. But if you could get that, you throw it in, you let it sit there, and look how big it gets after 50 years. Now this means you can't touch the money for 50 years. So obviously there's downsides to this. There's also, this is not something, again, we'll do any of the math on, but there's also this idea of inflation. $117,000 sounds awesome now, but in 50 years, that won't buy the same amount of stuff as now. That won't be worth, quote unquote, the same amount as it is today because of this idea of inflation. So there's other things to think about when you're saving like this, but this is the general idea. This math all works, all is what happens when you do compounding. But it's not so clear, cut, and dry as just put $1,000 in, look at me, I'm rich after 50 years. Well, there's other things to consider. But that's it. That's the math. And so that's the formula. If you are going to compound once a year, we've got the formula. So our formula once a year, so this is just being a little more specific now. So my formula for once a year is how much did you put in? So the notation here, which I'll introduce all the letters in a second, what they mean, is the amount of money you have in your bank account at the end of the saving is equal to the amount you start with times, and then you do 1 plus the percentage interest rate you're getting, and you raise it to the t power, the amount of years. So $1,000, 1,000, 1.10, that's me doing 1 plus the 10%. That's just that number. And then T was 50 years here. Boom, boom. Not a terrible formula for being able to do that. And then I can plug in any year I want, any interest rate I want, any amount of money to throw in at the beginning I want. I could try anything, and I'll be able to figure out how much money is sitting in the account then. So there you go. All right, so there are other situations that make this a little trickier. So we've got another formula, a scary formula here, that hopefully looks very similar to this one. A is the amount in your account after some amount of years, T years. That's equal to the amount you start with, P, often called the principal. We'll see that word later with loans. And then you do 1 plus, and now here is where things get tricky. This R over N. So why is this happening, this R over N? Well, the way that these things are often given is the bank will say, okay, here is your yearly interest rate. And that's R. R is your yearly interest rate. Okay. So, all right, great. My yearly interest rate is 10%. So does that mean every time you compound I get 10%? Well, sometimes. The R over N here is what determines what happens when you compound. And the reason that it's not always just R% is that you don't have to compound yearly. You can compound as many times as you want every year. So this number N here, this number, is the number of times a year the bank is going to do the calculation and throw money into your account. That could be once a year, like we just saw here. N could be 1, and you just get this formula. Or N could be other things. What's common for N? Often you'll do things monthly. We'll see some examples of that in a second. So then if you're doing things monthly, N is 12, because it's all about what happens in 1 year. If the bank is saying, okay, every month I'm going to calculate this, compound, and give you money, then it's going to do that 12 times a year. So then what happens with your interest rate? What the bank does is it gives you R. But if it says, oh, I'm going to do it monthly, then actually what happens is it doesn't give you the full R. It takes R and chops it into 12 pieces, right? That's R over N in this case. So in this case, if R is, we'll just do 10% again, then every month, so then these combine, every month you compound, but not at 10%. You do it at R over N, which would be 1.10 over 12. Okay, so this is just to kind of see the number as a decimal, which might be nicer instead of this fraction. This is 0.0083 forever, which if you like a percent to kind of compare back to, this is actually 0.83%. So each month they're actually giving you less than a percent. So you look at this, monthly 10%, oh, look at that, look at how crazy this was when it was yearly. They're going to do it every month for me? No. This is not exactly what happens. Instead, they take the 10% and say, okay, I'm going to give you this much first month, and then the next month I'm going to give you this again, and then again and again and again, and then 12 of those is a total of 10%. It's a little bit weird that they do it that way and don't just tell you what your monthly interest rate would be. Lots of things you could think about on why that's the case, but we can see this and know how it works now. So the annual rate is a helpful number, but it's not what actually happens in the formula if you compound more than once a year. So the formula again, A is the amount of money you have at the end of T years. T is the number of years you save. P is what you throw in to start. R is the annual interest rate. N is the number of times every year they compound. They give you the money, and then you just throw into the equation. That's it. And so I know that there's a lot here, but just start with the equations. Just start with trying. That's all you got to do. Just start with plugging in and seeing if you can get the right numbers. So example 2 here, zoom in a little bit. You got $1,000 again. You put it in the bank. They say annual interest rate of 10%, compounded monthly. Tell me how much is in the account after 5 years. So what I like to do whenever I know I have to use a formula, I write down all the parts of the formula. And then I write down what I know and don't know. I don't know A, because that's what I want to find, how much I have after 5 years. I do know how much I throw in to start. I do know the percent. I do know the compounding, how many times you compound each year. It's 12, because 12 months in a year. And it says after 5 years. Okay, I've written them all out. I plug it in. Boop, 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 boop. Okay, I don't see anything over here but numbers and math symbols. Multiply, add, divide. So then I feel good to go. I plug this into the calculator, and there you go. You put $1,000 in, 10% annual but compounded 12 times a year, and you put it in for 5 years, you'll end up with $1,645 at the end. There you go. So hopefully, it's not too bad to use as long as you start just practicing, get the hang of it. All right. So, okay, maybe you're saying like that's not that bad. Well, it's not. And so you got to think about what else I could do. What other kind of problems could I give? How else could I use this? Another way we could do this is by just switching up what information I give you and what I ask for. But we've seen this already. The formulas we were using before with percent increase, decrease, the distance formula, D equals RT, all of those, sometimes I gave you some information and left one of them blank and said find it, and then sometimes I switched it up, what I gave you and didn't, and you had to be flexible. Use the formula, plug in what you know, solve for what you don't. This works the same. There are more options here, but we're not going to do every possible combination of these things. So specifically here it says, and in general we could do this, right? It says, okay, there are 1, 2, 3, 4, 5 letters here in my formula. So just go back up here, right? 1, 2, 3, 4, 5 letters in here. And so I could give you a problem where, oops, went too far. I could give you a problem here where I gave you 4 of these letters, the actual numbers they are, and said go find the other. And I could leave off any one I wanted. I could say go find A, or in a different problem, go find P, or go find R, or N, or T. Now in this class, by hand, I'm only ever going to ask for A or P, by hand. In Excel, we're going to use Excel to be able to find T. So we can use Excel to actually kind of map this out, put this equation into Excel, and then find T. And it's not too hard to do that. It's possible to use math to find all of these. It's just, it's a little bit more difficult for some of them, and so we're not going to cover them all. But doable. So what does that look like? Example 3. So in example 3, it says you want to have $20,000 for a house in 10 years. And so talking about down payment. So you want to buy a house and you're going to put the down payment, $20,000 in 10 years. Okay, so what are we thinking? We decide, you know what? We're going to put some money away right now. So we're going to put away some money into an account, and that account has 5% interest compounded quarterly. How much do we need to invest today so that it gets to $20,000 in 10 years? That's our ultimate goal. So I write down all my letters. I say A is 20,000 because that's what I want to get to. P, how much do I have to put in at the beginning? I don't know. That's what it's asking for. R is my 5%. Now this is sometimes tricky. Quarterly, what does that mean? Well, quarter, what does it mean to have a quarter? It means you have 1/4. So, oh, there's 4 quarters. So that means that n is 4. It'll happen 4 times a year. T is 10 years because that's how long I want to wait. I plug it in and I get this equation. 20,000, my end goal, is P, my starting value, 1 plus my rate over 4, and then up in the power here is 4 times 10, n times T. So the way I usually do this is I'll type this into the calculator, the right-hand side, simplify it down, and then we've seen how to solve this. I was about to say 100 times. Maybe it is 100 times. I'm not sure by this point how many problems we've done that have ended like this. Number equals unknown times the number, divide. So we're going to divide. And when we plug this into our calculator, we're going to get $12,168. Okay, so what does that mean? That means if I want to get 20 grand at the end of 10 years with this account, I have to start with $12,000. And that's it. So we got to be flexible. I'm not changing up the equation on each problem necessarily. It's just I may change up what is given. So that's why doing this step here where you write down everything you know and don't know is really, really nice and important. So, okay, what else can happen? We've dealt with a lot now, right? So there's one more compounding thing I haven't talked to you about yet. And we're not going to go through the kind of whole big thing we did to get the first formula. I'm just going to tell you what the formula is. And depending on your background, if you've done any calculus, I can talk to you about this as an aside. Come to office hours and we can chat about it. But if you haven't ever taken a class like that, then you're just going to have to believe me about this kind of idea. So we'll play with it a little bit, but we're not going to go fully proving anything. So this idea that I keep mysteriously talking about is called continuous compounding. Okay? And so continuous compounding, continuous, like what does that word mean? Something continuously happening, like, okay, a lot, over and over and over and over again. And compounding, we've seen compounding. You're adding in the money. So I said, okay, consider investing $1,000 at 5% annually. So, get rid of that for a second. What does this look like? Well, there are options, right? So A here, I could do just my compounding can be annual or yearly. So we already did this. $1,000 times 1.05. That was our first example. After 1 year, this is all I have to do to try to figure out how much money I'll have. And I will end up here with $1,050. Okay? So that's if I compound just once a year. In the whole year, I just compound once. That's it. Okay, but there's other options, right? We could do it monthly. And I haven't really talked to you yet about the difference here between doing it annually and monthly. Like what's happening. So we'll check it out. Here's your $1,000. Okay. Now the formula is a little different. Remember, 0.05 over 12. And then this would be a 12 up here. Times 1, because it's 1 year we're doing it. So I should write that in. 1 year times 1 year. Okay, so we got to put that into our calculator. So you do, and this is something that, depending on your calculator, you might have to do some extra practice with. If you're using kind of just like a basic phone calculator, what I like to do is first plug in this, hit equals, then I do the exponent, hit equals, and then I multiply by 1,000. But if you're comfortable, you can just put things in all together. There's no reason not to if you're comfortable with it. Okay, so I ended up with $1,050 $51.16. So, what do we see? Same annual percentage, but the more I compounded, the more money I got. It's only an extra $1.16, but it's more money. More money is more money. Well, what happens if I keep doing this? What about daily? What if I compounded every day in 1 year? We can do that. $1,000, 1 plus 0.05, 365 days in a year. So that goes up there. Okay, and again, put this into our calculator. Again, you can just do what's in the parentheses first, depending on your calculator. It's a little bit easier for you. And then when we put it all down, we end up with $1,051.27 if you round. Okay, so we actually get more money again. Daily, we get more money. So then that's the question you might want to ask is, what's the best I can do? Is there a limit to this? If I do this every hour, is it going to be better? Yep. If I do it every minute, is it going to be better? Yep. How about every second? Also yes. How about every half a second? Yep. And every half of a second? Yep. Are you tired of me doing this? Yep. Well, that idea keeps going, and it goes, and it goes, and you can do better and better and better. And so the idea of continuous compounding is asking the question, is there some best case scenario that can happen to me? And it might make, you might immediately just kind of think like, of course not, because you just keep increasing. So how could it kind of stop in some way? Well, to convince you of that, check out what's happening in each step here. I went from annual to monthly, and I got an extra $1.16. And then I went from monthly to daily, which is a big jump. Like, I'm compounding much, much more. And I didn't even get a full dollar extra, right? I only got 11 cents. So this extra compounding, the more I'm doing it, the more money I make, yes. But the amount extra I get each time I increase the compounding, that's slowing down. That's getting smaller. And so because of this, because it's getting smaller each time, there is this limit to what can happen. And that is continuous compounding. So continuous compounding is your best case scenario of what could happen if you, and this is a weird thing to think about, I know, but if instead of compounding once a year, 12 times a year, 365 times a year, you thought of compounding an infinite number of times a year. I know. What? What could you mean by that? I know it sounds crazy, but this idea is actually very important, and you can use math to explore that question. That's why math is so beautiful, is that you can think of these questions that sound crazy, but you can use math to explore them and try to answer them. And that's what continuous compounding is. It's an answer to the question, what's the best I can do? And this is the formula you get. This is how you use continuous compounding to do this problem. You'll notice in my formula, PERT. You'll often hear PERT, biology, chemistry, economics, which is our example here. PERT. You'll notice there's no N, no more N, because N is gone. N is not a single number anymore, right? We just said, let's let N be infinite. I'm going to do it an infinite number of times. That's why there's no N anymore. N, trying to go to infinity, gets absorbed into your 1 plus and your rate, and they all kind of meld together and become this number E. This crazy number E, which is not so crazy. It's called Euler's number, and it's about 2.718. That's the number. So how do I use this? Well, let's do it with the example that we just had here, right? I have another example here, but let's just continue this one because I think that would be nice to see the conclusion of this. So let's do it up here. I've got my $1,000, that's P, times, now I'm used to putting 1 plus and then my rate and all that, but I'm not going to do that. Instead, I'm going to write E, the number E, R, my rate was 0.05, and then T was my time. And in this case, we were just doing 1 year. Okay? So, plug this into my calculator. Now, I think every single calculator that you could possibly have and be using for this class has E in it. You're literally just looking for the letter E in your calculator. So you do 1,000 E and then raise it to the power. And you end up getting 1051.27, and then this one over here we rounded up to get that. This one, it's 271, so there's a little bit extra, but we could go 27 and round down. So again, just a tiny bit bigger than the daily, but this number is the best you can possibly do. If you have 5% annual compounding, you put $1,000 in and you let it sit for a year. There's no way to split up the compounding over the year and do better than this number. This is it. This is the best. I know it's a crazy idea. I do not expect you to be able to fully wrap your head around this idea. All I want you to do is be able to read a problem, say continuous compounding, use this formula. That's it. That's all I'm asking you to be able to do here. It's just read the problem, continuous. Oh, that's the special one. Let me go get the special formula. Psh, done. So another example here. You can go through that one. Very similar. Plug everything in just like we did. It compares to a previous one where you can see that we make a little bit more money. So then the next piece of this is called an annuity. Now, an annuity is different because it's the thing that most of us actually do. So an annuity is a situation where you're saving, where you, instead of putting money into an account and just letting it sit there, which some of us do, of course, but often instead of that, what you'll do is you will consistently put money into an account every so often. So every month you put part of your paycheck, or every 2 weeks you put part of your paycheck in, and you're doing it consistently. Now, if you put it into something like a bank account that gets interest, we can deal with that. There is a note here that this equation is slightly oversimplified in that the number of your N here, the number of times you compound a year, has to be the same as the number of times you deposit a year for this formula to work. So if you're going to deposit money into your account every month, then for this formula to work, the bank needs to be compounding every month. It's totally something you could calculate if you change things up. But in terms of just formulas and using them, things are a little too complicated. We're going to use this formula and simplify things just a little bit. Okay? So again, I know this formula looks like a lot, but just piece by piece. A is the amount you have after T years. D now is the amount you deposit each blank, each month, each year, whatever you pick. R is your annual interest rate. We're used to that. N, the number of times that you compound and the number of times you deposit a year. So monthly would be 12 as an example. And then T is the number of years. So very similar setup, just the formula is different. And you got to really be careful when you're plugging things into this formula. All right? So what does this look like? Let's do an example. Example 5. We put $200 into a bank account each month, and the bank gives you an annual interest rate of 7% compounded monthly. How much money are you going to have after 5 years? Well, let's write it out. I don't know how much I have at the end. That's what it's asking for. I do know to put $200 in every month. I know my rate. I know it said monthly, so that's 12, and I know 5 years. Everything gets plugged in there, right? Boop, 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 boop. I plug in everywhere, and then I just calculate. That's it. I just throw it in the calculator. Again, you're going to want to be careful depending on the calculator that you have. Some options that you can do are just this piece. Do this first in your calculator. You don't have to, but could be useful. Do this first. Then you can bring this in. Do this second. And then once you've multiplied those, you've got a number, you can then divide. Bring that in. If you're going to do that, put parentheses around this. Okay? Useful. You really can't overdo parentheses. I mean, you can, but it's hard to do that. And most of the time it will be helpful for you. And so we end up with over $14,000. That's pretty good. If you can get $200 a month and save that every month for 5 years, you'll have $14,000 at the end, with if you get 7% interest. Again, that might be higher than you can actually find in like a savings account. Often saving accounts are pretty low. But this could be an investment you have, or doing things in the stock market, whatever it is. Think about that you're adding a lot in, of course. $200 a month isn't nothing, but you can really do some good saving if you consistently are adding a little bit and you let time have its impact. Time is good. So it's an annuity. That's the whole idea. Formula's a little wacky, I know, but you plug in, you write down what you have, what you don't have, you plug in, you solve, you're good to go. Okay, and so lastly, we get to loans. So loans are actually really similar to savings, all right? There's going to be some amount at the beginning, and then that amount is going to grow if you don't pay using interest, and it's going to grow by compounding. So you're going to compound the loan, and you often hear that as interest on the loan. All they're doing is compounding. That's it. So very similar, right? Now, we could do this a couple different ways. We could have a loan, take out some money, never pay anything until sometime in the future, and then just pay off the whole thing at once. That's possible, and we can calculate that very similarly to compound interest that we did right at the beginning. That would be very similar to that. The most common situation, though, instead, is to make regular payments on the loan. You take out some money, and then each month, usually, but you can do different things, you make a payment. Now, that payment goes towards paying off the principal, the amount of the loan to start, but also goes towards paying off the interest. And so that relationship is interesting, and we'll deal with that later when we do the amortization table. So we'll get there later. But in terms of kind of trying to do calculations with this, we have a formula. We can do it. So here's your formula. Very similar looking to the previous one. P is the amount you borrow to start. D is the amount of your payment that you're regularly making. R is your interest rate given annually. N is the number of times a year that is your loan gets compounded. But again, we're simplifying. We're also going to make that the number of payments. So the way we're thinking about this is the bank says, okay, I'm going to compound your loan now. And you're like, all right, here comes a payment. And then those two things are happening and happening and happening. Same interval. And then T, again, is the number of years. So what are the most common things? You're looking for either P, how much can you take out of a loan if you can pay this every month? This is the interest rate. This is the time. This is N. Or you could also do something like, I need to take out P amount of money, P dollars. How much do I have to pay each month to pay this off in 10 years, 15 years, whatever you want? So those are the kind of two most common ways to solve a problem with this. So example 6 is one of these. You got a $100,000 loan you want to pay off over the next 15 years. The bank says, okay, I'm going to give you an interest rate of 3%, compounded monthly. Find the amount you must pay each month. So, what do we got? $1,000 loan. That's P, the amount we start with, equals D. That's our regular payment. I don't know that, so that just is left as D. 1 minus, and then all this stuff gets plugged in. Here's your R, here's your N, here's your N, here's your T, all plugged in, just like very similar to the last problem. Again, though, I always take a step to simplify this in the calculator before trying to just do everything at once. But once I get that, well, would you look at this? Problem number 101 that ends up in the form number equals unknown times number. Divide. All you got to do here, divide. So just to write it out, so divide both sides, just like we did before, and you end up getting $690.58. You pay that every month. In 15 years, no more loan. There you go. So that is how we could figure out the monthly payment on our loan. So a couple things you can do with this in the amortization examples, but you can figure some stuff out here. Like, okay, how much did I pay? Right? I took out $100,000, but how much did I pay the bank back? Because that's not written anywhere. Well, what did I do? I took $690.58 of my money every month, and I paid it to them for 15 years. So this is how much I paid per month. Okay. Multiply that by 12. This is going to be how much I pay each year. So we're doing a little sneaky unit conversion in here, because the 690, you could think of it as a rate, a per month. So this is how much I paid, $8,286.96 each year. But then how long did I do it for, right? 15 years. So now times 15. Okay. $124,304.40. That's the cost of the loan. So you got $100,000 to do whatever you're doing with it. Who knows? Could be for a mortgage, could be a student loan, whatever it is. But then in 15 years, over the course of 15 years, you've paid off $124,000. So this extra chunk of money that you had to pay, this chunk here, the $24,304.40, that chunk here is the interest you paid. So that's how much you paid in interest. It's like what the cost of the loan really was for you. Okay? So that's what the bank gets. It gets $24,000 for letting you have its money over this time period. And that's how loans work. Now, of course, with everything we've done, right, real life has lots of different caveats to it. You set up a loan for 15 years, things change, right? Maybe you set it up so you'll pay $690 a month. Well, you could start making more money and realize, I could pay off my loan faster if I just pay more. What would you need to do to kind of figure out what's happening there? You could do some more of these calculations. Say, you know what? I actually have a new amount I can pay every month. So let's recalculate now how long it will take me to pay it off doing this. We could do that. We could just solve for t. Again, by hand, not very nice, but doable. Of course, you could go the other way, right? Say, actually, I'm not making as much anymore. What happens? Well, if I can't pay the $690, maybe I can pay some of that, and then it's just going to take you longer to pay off the loan. And so you've got to do that calculation now with a smaller payment. You can also refinance your loan. Let's say your credit goes up. Say, hey, I got this loan when I had not too great credit and I had to pay a high rate. Can I get a better rate now? Can I refinance this loan so I can get a better rate? That's always an option. If your rate goes down, your payment's going to go down if you keep the same time frame, so you can figure that out. All of these things are things that we can figure out, and we can use the formulas that we have, the formula I have here, plus the idea of the amortization table in Excel, which has some other formulas kind of baked into it, to figure all this out. The nice thing about the amortization table is that we can make these changes partway through paying off a loan, which is really neat, right? We could pay, we could go 7 years into the loan and then, oh, I got a raise, I can pay more now to get this over with quicker. Or, ooh, I have better credit, I can get a better rate. And so then we can figure out what things should look like there, because this table that we'll look at gives us how much is left to pay, which is not in here. This is not giving us any idea in 7 years how much of the original loan is left to pay. Because remember, each payment you make is part interest, part principal. So that's not in here. We've got to do some other work to figure that out, but Excel will do it all for us, which is pretty nice. So that's going to be separate, creating an amortization table. Go find that video on Lumen. You could check that out. That's going to be just part of your project. So your project will involve creating an amortization table for a specific loan that you're going to be taking out. Okay? So if you made it this far, good job. Remember, timestamps, use the timestamps to jump around here. Although, again, I told you at the end, but hopefully on the last video, if you watched all the way through and saw it and heard me say that, you remembered to do it for this video. So now I feel okay again. Although I will try to remember to say it at the beginning of the video for the next video. All right, keep working hard. Ask me questions with whatever you have.